Today we're going to extend a little bit into area, and we're going to put it all together in the next couple of days. So like I said, I do have your tests ready for you. I'm going to hand those back to you. Well, we need to work through a couple of examples here and make sure that we're staying on schedule and all that good stuff. This will probably be the tightest scheduled math class you've ever had. You don't have time to just say, hey, let's just take a day off. There just isn't time. So snow days are absolute disasters, terrible disasters. But we'll deal with it if it happens. We'll figure it out. So in that video, in the intro video, I talked and showed lots of like really simple pictures about left sums and midpoint sums and right sums and all that stuff. More often than not, though, those situations will typically be presented as a table. It's quick, it's simple, it's hard to hack. Some people have learned how to hack certain procedures with left and right and midpoint sums. These tables are unpredictable enough. And I say some people, I'm talking about like worldwide, not like students necessarily at Valor. And so they're usually presented as a table. But I would say that, especially when you're starting off, seeing it in a table might be kind of hard. And so translating that table into a graph might be a good move. So I'm going to do that here at the start to help us. And then I'll let you guys kind of run with the rest of it. So if I was going to do I was going to do a left sum and use 4 subintervals. I might want to try to graph this real roughly and just see what it looks like and use that as a guide. I know that I've got the point 018 and the point 132, the point 272. So that'd be like up there somewhere. I'm going to lose my scale here in a second. 5, 200 would be up there somewhere, and 8, 242 would be a little higher. Sort of okay? Close enough? Okay. So, maybe if you wanted to, you could connect all those points with a nice smooth curve. You don't really have to do, you don't have to do this, but you could. Okay, so if I was going to use a left sum to approximate the area under the curve, if you remember from the video, a left sum means we're using the left edge of the interval to tell us our height. So left sum rectangles would look something like this. We use the left edge for height, so on and so forth. And I would get to my 4th rectangle right there. And if I could just find the areas of those 4 rectangles, I'd be good. So you see what I'm trying to take the table and get it into a graph. You don't have to do this. If you can just see what you need to see from the table, I'm totally fine with that. But I thought I'd show this to you just so you can kind of see. So if I was going to do a left sum, so part A, I would say that my first base is how long? First base? 1. So I'd go with 1 times, what would I use for my first height? 18, yep. So I'd use this height for my first rectangle if I'm doing a left sum. So 1 times 18. What would be the base of my next rectangle? 1. Again, 1, right? We're going from 1 to 2. So you got 0, 1, 2, 5, and 8. So next one is a base of 1. What about the height for that second rectangle? 32. We're just going to continue to use the left edge of the interval because we're doing a left sum. What about the next 2 bases? They're the same, aren't they? From 2 to 5, 5 to 8, 3? Okay, so this would be plus 3 times something, plus 3 times something. What would be the last 2 heights? 72 and 200 in that order. Yep, so 72, 200. Okay, so that would be a nice example of a left sum. You can do some little order of operations, multiply and add. 50 to 266, 866. You would do it yet? Did I do that right?
Sounds good.
216 plus 50 is 266. Plus 600 would be 866, yes? Okay. All right, so there you go. You could say 866 and call it good. Okay, so that would be my approximation using a left sum. So for a right sum, isn't it going to be the exact same thing, except instead of using the left edge to determine the height, we use The right edge, yeah. So if you guys would take a minute, see if you can do a very similar process, different numbers, different details for sure, but try B, which is a right sum. I'll sketch that out up here, or I will try at least. So about a right sum, what part of a right sum is going to be exactly the same as the left sum?
The distances. Or like the x-values.
You got the right hand motion at least, right? Yeah, the bases, right? Yeah, the bases are all the same. So it's going to be 1 times something plus another 1 times something plus a 3 times something plus another 3 times another something. Okay. And really, all the heights that are going here for the right sum, they're going to be sort of similar looking too, but it's going to be like they're off by a little bit, aren't they? What would be my very first height that I would use? 32. I'm using the right edge. How about the next one? 72. And then, of course, the last one is one that we didn't use before because we were using all left edges before. This one will be 242. That make sense? I'll leave the arithmetic up to you. Yeah. I'm sure you are good at that. What do you think? You okay with left sums and right sums? Okay, so then the last one is a midpoint sum. Notice the instructions do change a little bit. They say use a midpoint sum and not 4 subintervals, but 2 subintervals to approximate the area with a midpoint sum. So see if you can figure out what that means, or maybe in some cases see if you can remember what that means. And I will try to reset. So we're doing a midpoint sum with only 2 subintervals.
Yeah, it's not a lot of.
It's only 2 of them,
add.
right? Yeah, a couple of things to multiply and add.
Yep.
Mister, so like if I add them and divide by 2, is that going to be
If you add what and divide by 2?
those 2 together
That would only work in one specific situation. You're talking about to get C?
to get like the midpoint thing if we're using midpoint?
Yeah, that would only work in one situation, and that's if we know that our function is linear.
Okay.
And we have no idea if it's linear or not. So we just got to take the numbers right out of the table.
Oh, that kind of makes sense.
Always, so I would say always, always, always take numbers out of the table. Never like kind of guess. Like, okay, so the table kind of did one of these, and so halfway between.
So
And
like if it's like that, and
you
then,
just got to take the numbers out of the table.
okay.
Yep, because we don't know what's going on between.
Okay.
We may or may not. For sure here we don't.
Okay.
All right, here are a couple of midpoint rectangles. So let's see here. It would be about here. What do you guys think about that? Do you see how those are 2 subintervals? So just like the left and the right sum are named for where we get the height, the midpoint is named for where we get the height. I tried to use the midpoint height to determine my height. So I didn't use the height at 2 or 8 or whatever. I used the height at 1 because 1 is the midpoint of that first subinterval. And 5 is the midpoint of the second subinterval. So I used the height at 1 and 5. Okay, so I'm not
Is that because 1 and 5 are
smack in the middle of those
the
intervals.
table?
Not in the middle of necessarily the table, but in the middle of the intervals within the table, right? So it said 2 subintervals and a midpoint. So if I decided to do like I don't know, maybe for some reason I decided I was going to set up an interval from 0 to 5. That wouldn't work because I don't have a midpoint for the interval 0 to 5. I'd need a 2.5 x value for that. Like if I just decided to set this up. Maybe I wanted to make these my 2 subintervals. So I'd have a problem because I don't have a 2.5 in there, and I don't have the in between the 5, in the middle of the 5 and the 8 either. So I'd have to rethink that and say, well, I can't use those as my subintervals. Hopefully, eventually I'd say, well, what if I did 0 to 2? Oh, look, there's a midpoint of that. What if I did 2 to 5 as my other one? Look, there's a midpoint of that. If you're going to use a table, you have to pull data out of the table. You can't make stuff up and say, well, halfway between 0 and 5 is 2.5, so I'm going to estimate that it's like 97. You can't do that. You only know what's in the table. So you got to make the table fit what you need to get out in order to answer the question. Does that make sense? Good? Okay. So here, it's just 2 of them. So it would just be 2 times 32 plus 6 times 200. So 1,264. That one's a little bit easier. Okay. Who knew? Geometry, right? And the simplest version of geometry, like can you add areas of rectangles? But they're obviously strategic rectangles. It's not just random stuff. Okay. We're going to keep building on this. So far, so good? I got 2 more examples I want to do with you here today. So let's do them. They are over here. Okay, so there's a bunch of stuff about sigma notations and summation formulas. I'm not going to get too stressed about that. If you want to read through this little box, that's fine. It's going to be easy for us to just jump in. So those that have had AB before, number 3, what's the key scary word? Riemann. That's somebody's last name. German guy from way back, Riemann. Very famous mathematician, actually. And so this is named for him. And this is going to be the foundation for doing definite integrals, which is a really powerful tool for us to be able to apply and figure out all kinds of stuff that otherwise we'd really struggle with. Okay, so this says write a Riemann sum to express the area under the curve f of x equals x cubed. Notice it doesn't say approximate or estimate the area under the curve. That's what we just did, right? We used these rectangles to approximate this potentially curvy graph. It doesn't say estimate anything. It says we want to write an expression not for an estimate of the area, bless you, but for the exact area. Make sense? Okay. So I am going to just do a rough graph here. I think we all know what a cubic looks like. I'm just going to draw myself a little graph here so that I can kind of illustrate with it. So here goes y-axis and x-axis. And I'm only concerned about the interval from 0 to 1. So I'm going to say that my cubic, of course, comes in from here, flattens out briefly, but then I'm only really concerned about, oh, it was so good until that last little part. So we're going to say this is 0. We're going to say this is 1 out here for our cubic, and we're going to try to build this out using a Riemann sum to actually get the true area. So what I'm going to do here is I'm going to put some rectangles in to kind of help us get an idea of what's going on. So here are a couple of rectangles. There's a little short one. There's a little taller one. And you can see how this would go. They just keep getting a little bit taller as we went. I'm just going to put dot, dot, dot. Okay, so I put dot, dot, dot because I don't want to paint myself into a corner with a certain number of rectangles. I want flexibility here. If that makes sense. Okay, so we're going to kind of build this out piece by piece, and I'll try to point out some of the easy parts and some of the harder parts of this. A Riemann sum is always going to involve a summation, and so to me, the easiest part here would be to start by writing that. We know that a Riemann sum is going to be a sigma. It's going to be a summation. So that's why I'm going to start. And then we're going to build this out. And we're going to, honest to God, I'm just going to try to use common sense. We're trying to add up rectangles' areas, right? And what is the area formula for a rectangle?
Base times height.
Base times height, length times width. Let's not overcomplicate this. I'm going to go with base times height, but length times width would be just as good. So we're basically going to be doing some sigmas with base times heights. And like I said earlier, I want to be really super duper flexible with how many of these rectangles that I use. In fact, what I'm going to say is I want to use n rectangles, where n could be whatever number that I want it to be. Could be anything, right? So maybe it's 5, maybe it's 10, maybe it's 1 billion, whatever. Could be whatever I want it to be. So here's the first thought that I want you to think about. With these rectangles, would you guys agree with me that all these little markings that I'm putting in here, aren't I marking the bases of each of the rectangles? Okay, so let's pretend for a minute that I was going to have 4 rectangles on this interval. If they were evenly split up, what would be the base length of each rectangle?
0.25.
0.25. Let's use a fraction, but I agree.
1/4.
1/4, right? What if I was going to use 10 rectangles? I was going to squeeze 10 rectangles in there. They'd all be how wide?
1/10.
1/10.
2/20.
1 million rectangles, they would all be
10/100.
1/1,000,000th, right? But what if I wanted to maintain this flexibility and say, you know what? I don't know exactly how many I want right now. I want to have n.
1 over n.
They would each be 1 over n wide. Does that make sense? Well done. So I'm going to start off by saying I want my rectangle's bases to all be 1 over n wide. Because I want to be flexible. I want to be able to do whatever I want with these rectangles. Okay, now the height is a little bit tougher. Would you guys agree with me that the height of each rectangle is essentially determined by the curve's y value? Is that a fair statement? Okay. So then I would say, since we know this curve, this blue curve is x cubed, right? Y equals x cubed. I would say that the height then is going to be something cubed, right? The height is based on the y value of the curve, and the y value of the curve is based on input cubed. Fair enough? So then the input. So this is where it can get a little bit tricky. And I'm going to come back around to this in a second because I got to start thinking about how is this sigma going to work. And I'll come back around to the input here in a second. The sigma, as you guys know, is going to start somewhere and then just keep adding and adding and adding until we get to a certain number of values, right? So I remember I want flexibility. So I want my top end of my summation to match the number of rectangles that I want. I want to have n rectangles, so I want to be able to add up all the way to those n rectangles. I don't want to have to stop short or have something not match up. We usually have an element. Are you guys okay with I? Sometimes it's j for like the element that's determining the summation. So we usually use I. I'm going to say I equals 1 to n, simply saying I want to start off with my first rectangle, and I want to go all the way out to my nth rectangle, adding up the areas each time. Is this making sense so far? Okay. So then back to the height. The way that I like to think about this is height is simply input cubed. And where I start with this, I'm going to try to use the same language I did last year. I'm going to start off with answering this question. What is the lowest conceivable input that I could have on my interval?
0.
In this case, it's 0. Sometimes it'll be something other than 0, but right now it's 0. So I'd say 0, that's the lowest possible input I could ever have on this interval, plus, and this is the trickiest part here. When I move from one rectangle to the next, so I go from this one to this one to this one, so on and so forth. When I go from one to the next, I'm basically adding something to my input each time, aren't I? Aren't I adding the width of a rectangle to get to the next rectangle? Does that make sense? So I'm going to say 0 plus the width of a rectangle. Wouldn't that get me to like the end of my first rectangle? Well, then how do we progress then? I got to have an I, right? Yeah. So if I go times I, This will allow me, because I know that my eye is going 1, 2, 3, 4, 5, dot, dot, dot. This will allow me to go from the first one, right here, to the second one right there, to the third one, to the fourth, to the fifth, to the nth. All the way out to wherever I want this to go. You guys doing okay so far? Have any questions? Santi?
Would that be like, if like the answer you get out of that, would that be overestimated because the rectangles are above the curve?
Well, it depends on how many rectangles we use. So let's go there. So let's talk about this.
The more you use, the closer you are to like the actual.
That's true. And we can use, I know where you're going with this, I think. We can use a left sum. I obviously used a right sum to model this, right? We can use a left sum. We could have done that. And what we can show that, I don't want to say this yet. I'll after I get this one more thing. We can show that certain things will converge depending on a certain pattern, so it really wouldn't matter. Anyways, so this right here is the formula for finding the area under this curve using n rectangles, right? So literally, if I wanted to use 10 rectangles, I would set n to be 10, and I would sum up 10 of these terms, and I'd get some number, and I'd say, well, that must be the approximation using 10 right sum rectangles.
Why does it stop at 1?
Why does it start at 1, or why does it?
Why does it? What makes that expression stop at 1?
Are you talking about this right here?
How does it keep within the interval? Yeah.
Because we were just told, let's find the area in between 0 and 1. Like if it said in between 0 and 2, that would change things a little bit, right?
No.
But 0 and 1 was set by the question writer.
Would it be 2 over n?
Yep, it'd be 2 over n.
Oh, okay.
Yep, a few little details in there were changed, but it would be still the same concept.
Gotcha.
Good question. Yeah, anybody else? I like what-if questions, right? Or why is it that way? Because it could just be set by the question writer, or it could be a kind of a procedural idea, conceptual thing. Anything else? So I still have not arrived at an actual exact area, because the number of my rectangles could be like 10 or 20 or 30. How many rectangles would I really need in order for this to be a perfect exact area? Say again? Oh, infinite, yeah. But I can't just say, hey guys, let's plug infinity in. What's the only way? Yeah, you said it. You have to use a limit. So I'd come back over here to the front and I'd say, well, the only way for this to really work for what I want is I'd have to say the limit as n heads towards infinity of that. Forrest. Right sum or left sum?
Yeah.
So let's talk about this. This goes back to Santi's question. The short answer is it really doesn't matter, because I want you to think about this. I'm not going to rigorously prove this right now, but just think with me for a second. As the number of rectangles heads towards infinity, isn't the width getting closer and closer to a very specific value? What is it? 0, right? So as n heads towards infinity, this base length, this width, is heading towards 0. So if you start to think about those two edges of each rectangle as they squeeze down tighter and tighter and tighter, get closer and closer to 0, it's not really going to matter if you had a right rectangle or a left rectangle. It's just going to be the same thing. So you can actually prove that they converge.
So you're saying they're a lot of
We're assuming what?
like they're like infinite n.
No, we're not assuming anything. We actually put that in there ourselves. We're saying, what if we make the number of rectangles head towards infinity?
Oh,
That's the only way to get the exact area.
okay.
Yeah, because if you don't have that on there, now a right sum versus a left sum will very much matter.
So we're using the right.
It doesn't matter. I could use a right sum or left sum to start this off, but if I put this on the front, it's going to be the same thing,
Okay.
either way.
Yeah, but we are using the right sum, right?
Yeah, but it doesn't, so we are using a right sum. I could have used a left sum.
Okay.
I could have, and my point being that if I use a right sum or a left sum, either one, and then I put that limit as n goes to infinity on the front, it really didn't matter what I started with, because all those rectangles are getting squeezed to a width of 0 anyways.
Okay.
Does that make sense? Okay. Do I want to say anything else? Do you have any other questions? Okay, so this right here that I'm going to put in this lovely pink box, or this lovely pink box right here. This is what we call a Riemann sum for the area under the curve. Nice color, huh? Yeah.
Oh, a really good box.
I got a box tool on there.
Draw it.
Yeah, you can draw all kinds of boxes. I would like to take credit, but I can't. Okay. Anything else besides the awesomeness of my box up there? Okay. So why don't you guys try the next one on your own? It's a little bit different, but it's similar enough to where it should be a good, worthy exercise. I gave you a graph here. Notice that the boundaries have not been set from like 0 to 1 or 0 to 5. They're from 1 to 2. So the 1 to 2 will be different than the 0 to 1 that we just had. A little bit of a different setup. So see if you can think that through, and we can check some answers, and this will be it for us for today for any new stuff. Formulas that we don't have to do. If you're curious, you can run these all the way through and actually find areas using those summation formulas. I would say it's not very complicated, but it kind of is, only because of all the little symbols that can get lost. So anyways. So guys, I'll just write it up here and see what y'all think. To me, I'm going to always start off with the easy stuff. And I think the easy stuff is, it's going to be limit as n goes towards infinity of sigma from I equals 1 to n. So I know that a Riemann sum, or using a limit process to find area, we're always starting off with that. What I think is the next easiest would be the base length of each rectangle. Did you all have 1 over n?
Yeah.
For the base length?
Yeah, I did.
1 over n. And then, of course, and now 1 over n being that it might be tempting to put 2 over n, right? But remember, the full interval width is just 1, right? From 1 to 2 is 1. So you would divide it up into n rectangles. They would each be 1 over n wide. If the whole interval was 5 wide, then it would be 5 over n, etc., etc. Okay. What is the lowest conceivable input we could have for our height? So it's going to be 4 minus something squared. How low could we go on our interval on the input?
1.
1. So it's going to be 1 plus. Now, each time I move from one rectangle to the next from left to right, I'm going to add something. I'm going to add a width of a rectangle. Yeah, so it'd be plus 1 over n. But then I always have to multiply that by I, because I want to be able to actually progress all the way across the whole region to get all of the area instead of just the first little part. At this point, I've got it. You can do, the simplifying, just saying the simplifying is not complicated from the perspective of what to do. You just need to do some binomial expansion, some distribution and all that. But there's a lot of little symbols that can get lost in the mix. I'm going to leave it at this right here. This is all you'll really ever have to do is like write a Riemann sum or match a Riemann sum to something. And we'll continue to do this when I see you guys again next week. Are there any questions before we close this one off?
No, sir.
Okay.
Not today.
All right. Fair enough. So why don't I hand back your tests to you?